In the last video, I kind of proposed a hypothetical example of heating up water from 50 degrees Celsius to 150 degrees Celsius. Let's do that as our example. So you see the specifics of it laid out here and some of the physical constants we'll need reported in the question. So how do we do this? All right, well, first of all, in my opinion, these kinds of questions are actually, they can get very confusing, surprisingly confusing. And it's really easy to get mixed up in these kinds of problems because you're going to be, as they get more complicated, you're going to be working with lots of different temperatures, lots of different specific heats and heats of transformation, and you're just going to have numbers everywhere. And if you don't have an extremely organized, methodical approach, you're going to be in trouble. But if you do have a very organized approach, these are easy. So let me show you after, to be honest, this is a topic that I did horrible on as a student. And I had to develop my own method for solving these things methodically before I finally started to get them right every time. So let me show you the method that I developed for myself of how I do these problems. I like to make a little flow chart. And this flow chart is going to walk me through the step-by-step of this process, one thing at a time, one cue at a time, so that I can see the steps of the process first. And then once I can see what the process is, I know how to do each individual calculation on the list. Okay, now what I mean by that is the following. This is going to be, in total, a 3-step process because I know that the boiling point of water is at 100 degrees Celsius. So since it's going from 50 to 150, I can see that it is passing through the boiling point. So that means there's going to be 3 steps to the process: heating from 50 to 100 Celsius, the phase transformation, and then heating from 100 to 150. So when I draw my little flow chart I'm mentioning, it's going to look something like this. Okay, so in this box here, this is going to be my initial state. And there's basically 3 things that are important about the state of the object for these flow charts. The mass, that comes into play, the state of matter, and the temperature. Okay, so here I have 2 kilograms is the mass. I like to write all this in here just to make sure. It's liquid water. So you can write liquid here, or I'm just going to write water because I know water is a liquid. And the temperature. So the water is at the initial temperature of 50 degrees C. Okay, now that's my initial state. Now I transform that into a second state. So I draw another box in my flow chart. And my second state, it's still 2 kilograms. Obviously, the 2 kilograms isn't going to change, but it's helpful to write it down because in the problems we'll be doing a little bit later on, you might have multiple masses floating around. Now I have to ask myself, is it still staying as water or is it steam? And the answer is it's still staying as water for now because I haven't reached 100 degrees Celsius yet. So it is still liquid water. But now I've heated it up. I can't heat it up beyond the boiling point, so I'm just going to heat it up to the boiling point here. So I'm heating it up to 100. Why 100? Because 100 is the boiling point of water. And this process going from 1 to 2, there's going to be a Q associated with this. Let's call it Q1. And I'm also going to make note for myself, this is a temperature change. So this is going to be calculated via the MC delta T formula. Okay, now I keep going. The next step in the process is going to be, make another box. It's still going to be 2 kilograms. Now, is it water or steam? Now it's going to be steam because it's already at 100 degrees Celsius. This is going to be the phase transformation. What's the temperature? It's not 150 yet. We haven't started heating it up yet in the sense of raising the temperature. We're still at 100 degrees Celsius because, and this is like the most important thing to sink in to your brain for this, You cannot do a phase and the temperature change in the same step. You have to pick, is this step going to be a phase change or is this step going to be a temperature change? It can't be both. I did a phase change here, so that means the temperature remains the same. So this one's going to be calculated with the phase change formula. And now we can finally start to heat it up beyond 100 degrees Celsius. So here we will finally reach the final state, which will be 2 kilograms of steam at 150 Celsius. And this is going to have a Q3, and this one's going to be calculated with MC delta T. Okay, so that's what I mean by a flow chart. I now have this laid out in front of me. I now have my thoughts organized. When you first read this question, it might not even be clear to you that this is going to be a 3-step process. And like if I'm grading this, you know, as a grader, 75% of students are not going to do a 3-step process for this. They're probably going to do either a 1-step process and totally ignore one of them, or they're going to do this as a 2-step process and try to heat from 50 to 150 all at once. You have to break it down step by step by step. Okay, now that I know what I'm doing, I can see the trajectory of this problem. I have 3 things to calculate: Q1, Q2, Q3, and then add them up. That I can do. Now, this is the beauty of this flowchart method. Now I can totally ignore Q2 and Q3. Focus your eye right now completely here. That's the only thing you need to look at, those 2 boxes, because now I'm calculating Q1 only. So I can see here, I'm doing it as an MC delta T. I already established that. Okay, M, I can see here, M is 2. C, okay, which C do I use? Because there were 2 C's given in the problem. Remember, C is the specific heat. I can see that from here. I'm interested in water right now. And it should be the same in both boxes if you're doing a temperature change. It's water at the beginning, water at the end. So I use the number for water. I have to convert that to SI. So it becomes 4190 joules per kilogram Kelvin. And then my delta T, there's my final temperature, 100. There's my initial temperature, 50. And you will notice I never had to look away from those 2 boxes at the flow chart in order to calculate this Q. That's the beauty of it. I was able to just narrow my vision to one small, manageable, bite-sized piece of the problem and just do that by itself. And then we'll work on the next bite-sized piece in just a minute. Okay, so if I crunch these numbers, I get 4.19 times 10 to the 5 joules. Remember, numbers are going to be big when you're working with heat. Okay, there's my first Q. Second Q. Actually, let's switch pen colors just to emphasize this. Switch pen colors. Q2. Okay, now for Q2, I have my eye just on these 2 boxes. Okay, and I can see from these 2 boxes, first of all, I'm doing an ML. I already established that. Now, whenever you do an ML, you have to stop for a second and ask yourself, do I need to put a negative sign in here? So I have to think, water is going to steam here. Should that be a positive Q or a negative Q? Water going to steam has a positive Q because water has to absorb energy in order to turn into steam. That's why you have to put it on your stovetop to boil it, because it has to absorb energy from the stovetop. So that a positive sign is okay there, so I don't have to do anything. The mass is still 2. L, which L do I use? There's 2 given in the question. This is water to steam, that's liquid to vapor, so I'm going to use the vaporization. And that also has to be converted to SI units because it was given in kilojoules. So this will be 2.257 times 10 to the 6 joules per kilogram. I picked up 10 to the 3 from moving the decimal point and another 10 to the 3 going from kilojoules to joules for a total of 10 to the 6. Okay, and that gives me 2.257 times 2 is 4.51 times 10 to the 6. By the way, just as a side note, you'll notice that the heat of transformation here is 10 times larger than the heat from the temperature change. Heats of transformation tend to be big. It takes a lot of energy to change phase, especially from liquid to vapor. Okay. All right, let's get a different pen color, about pink. So now we're going to work on Q3. So I just keep my eye on these two. Q3, this is an MC delta T. M is still 2. So for C, which C do I use? You can see here I have steam and steam. So I use the C for steam. So that's 2,000 joules per kilogram Kelvin. And my delta T, my final is 150. My initial is 100. So 2 times 2,000 times 50 is 2.00 times 10 to the 1, 2, 3, 4, 5. And then my final answer, the total heat required is going to be the sum of these three numbers, Q1 plus Q2 plus Q3. In this case, they're all positive, but you would add them including the negative signs if you needed to. And 4.51 times 10 to the 6 plus 4.19 times 10 to the 5 plus 2 times 10 to the 5 gives me 5.13 times 10 to the 6 joules. That's my final answer. Okay, so this is a long, tedious problem, but if you break it down with that flow chart, to me, it's very manageable. Every single step is manageable, but you have to organize your thoughts about what are the steps you're going to need to do. That's really the key point in my mind.